So we can I already progressed. So Tony, I'll let you kick it off of our two-part presentation today.
Okay, thank you, Jay. So I'm going to talk a little bit about some underground transmission cables, which were fairly short, but there was an interesting case. And ultimately, the case is about you need to not just follow procedures, but have people who know what they're doing. Because anyone can sell you a box with lights on, and what we're really interested in is managing the assets. So, Jay, if we go to the next one, please. So many years ago, I did work at National Grid in the UK, substation specialist, transformers, breakers, partial discharge, cable ends, and so on. What we're showing here is a short 300 or 400 meter cable on a particular site. And you've got a guy looking at the cable ceiling end there. And the cable is one of those oil paper construction with lots and lots of layers, PVC outer. It's 275 kV cable. It's been in service for more than 40 years. Nice piece of cable. It does its job, does its work. The line comes in on the right-hand side to the line ends. You've got 275 kV overhead. Goes to the cable ceiling ends along underground across the station. And comes to a circuit breaker ceiling ends where you've got the oil expansion tanks. And it's from there that we would take oil samples on a regular basis so that we could detect market sparking or deterioration within the cable. Okay, so down one, please. Thank you. We also look for oil quality. So we had a lot of experience with cables. Cables at National Grid UK were the largest single asset in value. So if we looked at power transformers, we had more money in cables. Usually people think it's transformers. We had a lot of experience with using these cables in a variety of locations, in tunnels, in direct bury, and so on. The main ring around London was a 400 kV cable. So that was a lot of experience that we had with dealing with issues with cables. So we knew about DGA, we knew about oil quality. So next one, please. The gas alert comes in. So this is from a routine sample. We did have cables where we had online dissolved gas analysis. We would use either hydrogen-only monitors or composite gas monitors, depending on what we were thinking the cable was likely to fail, what the mode would be. So we had expectations for each cable, what the likely failure mode would be. We had plans for reacting to those. Next one, please. And when that alert comes in, we would then apply technology in a variety of different ways to try and learn a little bit more about what's going on. We can't necessarily test the cables themselves right down in the ground, but we can go to each end of the cable, and that's where we found most of the failures were likely to occur. So first one, please, Jay. So we do a thermography on either end with the cable live, no indications of any problems. Next one, please. We do a corona cam, see if we get any arcing or sparking above ground. Nothing there. Next one, please. Partial discharge using a PD detector, fairly common device. Nothing showing at the circuit breaker end, but at the overhead line end, there was some significant partial discharge. Phase results showed some arcing and sparking. One more, please. Ultrasound didn't show anything while we were there. So it's important to know that with partial discharge, it can be intermittent. It can have characteristic where it appears for a while and disappears, and it depends on the load on the cable. So we have to be very wary of just automatically saying the problem is definitely exactly where we think it is. But we have very good information. The DGA in the cable is high. The partial discharge sensing shows a problem in that area. We've got 2 independent tests. We're going to go and do something. Next one, please. So diagnosis, we've got a problem in the line side cable ceiling end. 2 independent tests. Next one, please. So we decided to take the cable out. And I must thank Carl Johnston, a colleague at National Grid many years ago, who's continued in this field, as he was the one who was involved with this mostly. And taking a ceiling end out, taking it apart is a high-cost job. You're taking the cable out of service. You've got to do the oil management. You've got to do the safety. You've got to do the site supervision. It's a high-risk thing because it's intrusive and you can damage the cable. So it's not something to be taken lightly. And as a consequence of finding partial discharge and high gas, we went in. Okay, next one, please. Hey, what did we do? Strip down the paper, got down to a point where we could find the insulation was actually failing. And you've got arcing marks, you've got burn marks within the cable sealing end. So we know what we have to do to fix it. We're going to take that on, we're going to fix it. Okay, next one, please. So just to make sure, we took a sample from the line cable sealing end, because if the DGA at the circuit breaker end was high, we would expect it to be similarly high at the overhead line end, as it then migrates across and diffuses through the oil in the cable to the oil containment tanks on the side. There was no requirement to do this, but the engineers on site decided that this would be a sensible thing to do because we found the problem. This is only going to confirm it. It'll make life easier. Everyone will be happy. We go home, know what we're doing. So they took a sample. Next one, please. And it was lower, way lower than on the other side. At which point you have to do some head scratching and say that this then is not the source of all of the DGA that we've seen in the expansion tanks. We've got a problem. We think we fixed it, but this is not necessarily the source. So we're going to go and have a look at the other end again, please. And the decision was taken to extend the outage and break down the other cable sealing end and see what we could find. I mean, to a degree, there's clutching at straws, but there's also a whole safety aspect of this that we really don't want to put a line back in service where we have high DGA and can't explain it based on the fix that we've put in place. Just pure risk analysis. Next one, please. Taking the cable sealing end apart, we found burning, high potential of failure, all sorts of issues that were then addressed by fixing that and would not have been if we hadn't done that DGA sample, and we would expose people to a far higher likelihood of a cable failing on a substation with man. Next one, please. Catastrophic failure avoided. Okay, one more. So this is just an illustration. It's actually a quite separate case on a different continent of oil seepage from a cable. This is the cable as it came out of the ground, and you can see the metal lead cover, and oil is coming out from that cable gently, slowly but surely. In service, it's not actually live at the moment, but the cable in service would have been seeping oil into the ground. So this is the kind of thing that we're trying to avoid. In this case, this pitting was caused by the direct bury, and on a 275 kV cable, you do have a PVC wrap around that, but it still does have that problem occasionally within the cable. Cable sealing ends are the far more likely failure mode, but they've got problems. In this case, we had a save and everyone was happy. Questions on that? CSE is cable sealing end. And oil fill cables, you have to have an end which you can seal so that the insulating oil doesn't get out. So that's why it's called the cable end, but cable sealing end as opposed to just a standard cable termination. If anyone has any questions, I'd appreciate those. Otherwise, we'll go with the J and then move on to some partial discharge efforts.
So Randy, if there are any questions, pipe up, or maybe I can go through the next sort of case study and we can discuss questions at the end. So the next case study we wanted to present was a little bit about a global monitoring architecture for underground buried cables that we're working on. This architecture has been deployed, and we have some interesting results for it. We're focusing on underground cable in this presentation because while a majority of transmission cables are overhead, the cost of underground cables, just deploying them, maintaining them, is significantly higher than the overhead lines. So there's sort of an economic ROI that sort of makes sense with underground that isn't available to the overhead transmission lines. But when we're talking about most buried cables that are going in today, and specifically types of cable not oil filled, like XLPE, we have a lot. Partial discharge is really the primary way that we look for the insulation and the health index of that cable. We do that throughout the entirety of the life cycle of cables, underground cables at Doble. And if we think of, Tony and I have had some discussions about this curve and if it really is applicable to certain cable assets. But with many electrical assets, we think of a common risk curve of when we put a asset in service with infant mortality, the life of the asset having random failures, and then some sort of increased failure with aging. A lot of what we do with condition monitoring, specifically on cables, is to bring that risk down. And we can do that on all levels or all stages of a cable's life. And that's important because if you look at the US across the 600,000 plus miles of transmission cable, more than half are into their second half of expected life or useful life. But when we put cables into service, we often do a high pot PD test to identify and make sure that there's no PD or imperfections with the insulation on the cable. We do this with a resonant test set. And we're looking for the terminations, the joints connecting the cables. And we typically do this with portable PD equipment, PD monitoring equipment. When the cable itself is in life and in service, we can do PD testing. Oil-filled cables is actually really difficult to do PD testing on in the middle of the cable, which is why having oil samples and Tony's presentation is very relevant to oil-filled cables. But also, we can take that same core technology that we would use for periodic spot testing, and we can permanently install it. And this architecture that we're talking about is a permanently installed PD monitoring system for transmission buried cables. When you think about buried cables, between substation and substation or between point A and B, the cable lengths are actually smaller segments that are spliced together. And those splices and the terminations are the most common points of failure on a cable. And so when you think of a splice and we think about overall budgets for this type of thing, it's important to realize that, when we're looking at a splice, replacing a splice, a planned replacement, is often around the cost of $60,000. And that's for a planned replacement. When we have failures on underground cables, I think the average is 4 to 9 days because of locating the failure, replacing the cable, replacing the splices. So these underground assets are something that we really want to take care of and monitor in as much real time as we can. And so the architecture that we proposed was putting in partial discharge monitoring at both of the terminations and also as well inside all of the splice faults. Now, the splice faults can look very different depending on where you are. Here is a picture of a 138 kV XLPE cable on a rack. That larger bulge in the middle is actually the splice itself. And oftentimes these vaults are used to protect that splice because that is the most common point of failure. You want to be able to access that. If you need to replace cables, having an easy ingress is useful. But in certain areas, in more rural environments, maybe you don't need an entire vault or underground vault, and just a sort of a shallow buried vault would be just fine. In both of these cases, we can put partial discharge monitoring equipment in here to monitor that splice. The way we do that is by using a PD acquisition unit embedded inside an IP68 enclosure. That's really important because all of these vaults are, as we all know, fill up with water. They can be dirty environments. So all of the system is IP68 rated. But effectively, we have the PD acquisition unit that connects to a sensor, HFCT, standard sensor, and takes up to 100 megasamples per second when we're doing an acquisition. And we take all of that data and we can process using industry common and some proprietary functions to look at the PD activity on the cable, and we can do that in near real time. The sensors themselves are typically HFCTs that we install on the ground, the ground leads coming off of the splice. So here in this picture, you can see highlighted in red different examples of where we would attach our sensors to the grounds. Oftentimes we can do that right in front of the cross-link or cross-bonding link box. But we can gather all of this data and provide real-time asset health information on the health of the cable using PD. Now, something that we're experimenting on, or not experimenting, but we're actually deploying today, is the infrastructure to do PD monitoring and continuous monitoring on underground cable is sizable. And while we're there, we're looking at what other things we can bring into monitoring that address the total cost of operating a system. So in addition to asset health, how can we bring in operational parameters? So we've evolved the PD design to actually include multiple sensors and multiple inputs that could actually bring other parameters. So for example, right next to where we put on HFCTs to get information about partial discharge, we can also use Rogowski coils to get current information of the current traveling through the grounds into the cross-bonded link box. This is really useful because now we can provide information about, is the cross-bonding link box working properly? Are we grounding out any induced currents coming or induced voltages on these cable runs? We've also included video cameras inside some of these vaults, both video and infrared. The application for this is oftentimes we have requirements to inspect our vaults. And if we can do that digitally from our laptop, we can save a lot of truck rolls and time. And the infrared is a nice added feature because we can point that right at the splice and see the temperature of that splice to make sure that everything is in line with what we would expect. PD monitoring is the best input that we can have into the insulation of the cable system. And so that's really going to give you the information and the warning about potential problems on PD. And we use displacement and vibration sensors to actually make sure that that cable, when it's installed, is staying on top of the cross arms, and also that there's no external interference with that cable, whether it be construction, street work, road repair, anything that might impact that critical infrastructure. So we've taken all of these different elements and we've tied them into our PD hub and bring all of this data back. So conceptually, what it looks like is inside of that manhole vault, we have the infrared sensor right in the middle pointing at the cable splices, video cameras on either side to give live video feeds of that for inspection or other purposes, and a series of sensors mounted, once again, all in IP68 rated boxes throughout the system to provide that vibration, displacement, and other sensors. And really the goal is to say, how can we take other operational expense about owning and operating these costs and integrate it into that asset health system? In addition, we've worked with partners on this project to bring in other elements. So while all of the information that we provide through PD, vibration, displacement comes into a single dashboard, which is called T-SCADA, we also work with partners that provide DAS and DTS, which is distributed acoustic sensing and distributed temperature sensing. The temperature sensing is really interesting because that allows you to use a real-time temperature rating on that cable itself. So you can actually have a really good understanding of proper loading and get excess capacity through the system without exceeding thresholds. And the distributed acoustic sensing will actually pinpoint if there ever is a failure on a system. It will tell you exactly where that failure happens, which can speed up your time to recovery. So we've integrated all of these different sensors and all these different software platforms into a single GUI for asset health maintenance. And it's a project that we are doing flagship projects in North America, but we have lots of experience across the globe with PD monitoring. So it's a tried and proven. Everyone here who's worked on cables is familiar with high pots and PD testing, but doing permanent installation is something that we're working on across the globe. With that said, we've presented two sort of different architectures, both surrounding underground cables. And if there are questions from the audience, I think Tony and I would be happy to answer them.
Okay, we had one question. What does CSE stand for? Is that cable sealing end?
Correct. It may be a British term, I'm not sure. I've not seen it in many places, but the cable is oil filled. And when you have, for example, cross-linked polyethylene, XLPE cables, you can just bring them up, wrap them up, and away you go. The old oil cables, they generally need to have a sealing end to make sure the oil doesn't go where you don't want the oil to go.
What is the failure rate of that kind of cable? And what are the usual typical causes of it, of the kind of failures?
So oil fill cables tend to have two failure modes. One is at the ends due to either poor manufacture, poor maintenance during life, or just, for example, ground subsidence, stretching the materials and causing the cable sealing end to start to come apart. Second most common is human interaction by people digging into them. And the third most common tends to be some minor impact on the cable from possibly digging, possibly animals, possibly something else, which has got involved with the cable, has damaged the PVC's teeth, and you get water ingress, water treeing, and the cable starts to disintegrate very quickly.
Are there manufacturing defects? Is that what percentage of failure is from manufacturing defects?
And I'm very wary of putting that in public, but somewhere around about 0.5 to 1% would be related to things that you could have identified at the outset if you'd looked for it and found it.
Mm-hmm. And installation, is that an issue? Also
Not
in
usually,
failures? Incorrect
no.
installation, I mean.
No, they're usually very well managed. All the teams I've ever seen putting these together are very professional. They know what they're doing.
Uh-huh.
What we have found over the years is that the larger voltage cables with oil filled are being replaced by cross-linked polyethylene. So they did that, for example, around London in the UK, where there was a whole 400 kV oil fill cables, some of which went along canals, and they got replaced by polyethylene.
What percentage of cables have cable monitoring?
Generally,
That's something I'm not familiar with.
I'll leave Jay to answer the more general question, but for the oil-filled cables, there's a lot of monitoring goes on, not usually multi-gas, but of the DGA, so you can work out if something has appeared somewhere in the cable and go from detection to diagnostics to try and work out what that is.
Yeah, going to the non-oil filled, the percentage is very low. Generally, every single cable when it's put in test gets high pot PD tested, and oftentimes there's periodic testing. Periodic testing and continuous monitoring go hand in hand, but the number is certainly low as a percentage, but we see a lot of interest growing.
So there's electrical issues show up in the monitoring of the oil in the cables. Is that similar to transformer oil monitoring?
It has a lot of similarities, yes, in that your partial discharge or your arcing and sparking will produce byproducts from the breakdown of the oil, which will then diffuse through the whole oil volume. If you have paper wrap cables as well, they will have some of the carbon monoxide, carbon dioxide Chris Rutledge was talking about before.
Right.
In terms of degradation modes.
I was going to ask Chris this, but I'll ask you, Tony, about this. Why is paper still used as an insulation medium? Aren't there any other materials that they can be used that would be more effective than paper because of the moisture content of paper even after it's dried?
So there are some that you'll find in more polyethylene type of insulation wraps, but paper itself for large transformers is extremely cost effective. And for the weight of the paper, for the cost of the paper, nothing's been found which is of the same capability and would be the same volume, as it were, so that if you use something else, you might get a transformer 3 times the size. Not necessarily any more reliable.
Is that the same with cables?
Cables generally had started out as oil filled at the very high voltages, but they're now moving a lot more to crosslink polyethylene and have done for a good 15 years now, 20
Okay.
years. So the technology has moved on from the oil for that. One of the
Okay.
things I would note is substation asset manager and distribution line asset manager for National Grid in the US for 5 years. We would find cables which are 80 and 90 years old come out of the ground, direct buried, and they look the same as the day they went in. And we find 40, 45-year-old cables come out the ground and they look like they've been there for 1,000 years and they were still in very poor condition.
Yeah.
So it's difficult to predict what condition a cable will be in without having a very good knowledge of its initial environment and how that environment will change.
All right.
Bathtub curves.
Okay, so here's a question. What DGA gases and levels are a cause for concern in cables?
So you can do this similarly with bushings at the start. You test it and you expect and you would assume that there is virtually no dissolved gases in there. So the appearance of dissolved gases implies that you've got some problem which has generated over time. You will get some breakdown at lower temperatures of the oil possibly, of the paper possibly in an oil fill cable. But you've then got to take that as a slow degradation. What you're looking for is a sudden rise in any of the key gases that you'd expect in a transformer, much as Chris talked about before.
Okay, Isaac, you have a question. How is associated fault-like voids being taken care of?
The void you would get in crosslink polyethylene cables. And that's where Jay and his system of extreme sensing would come in.
Okay, all right.
Yeah.
Okay, there's no other questions. All right, that's great. Thank you, gentlemen, very much. We're waiting for Dr. Prasad from Integrated Engineering Software to show up. He was supposed to start in 5 minutes from now.
Can I give you a little word on bathtub curves then, Randy?
Sorry, go ahead. Tell me again.
Could I give you a little word on bathtub curves then,
Sure,
Randy?
yeah, go ahead. Let's do that.
So the back people remember bathtub curves because they've got the word bathtub in them.
Yeah.
When Nolan and Heap in the 1970s developed that curve, that was one of 6 curves. And the bathtub curve applies to 4% of asset types. And that's been repeatedly done over years, 4%. When you apply it to power transformers, some people have found that it seems reasonable. When I was at Grid US, we did a very detailed analysis of transformer failures. And we found that after 60 years, we had not reached the far end of the bathtub. And it was very likely by the time we got to that far end, we'd have no transformers left just due to random failures in the middle stage of the life. So you've got to be careful about applying bathtub curves because it then produces models of failure which expect a rise. Now, Chris earlier said in Memphis that that's what he found. I think maybe that's what he found. We didn't find that. But there's a technical brochure from McGrail a few years back, technical brochure 642 on transformer reliability. And that one found very little evidence of a bathtub curve for most of the organizations involved. So I'm not saying Chris is wrong. I'm saying in his case, he found it to be applicable. But in the case of National Grid US, we did not. In the case of National Grid UK and many other utilities, it didn't seem to apply. So when Jay showed his little chart of a bathtub curve for cables, the first thing I did was step back and say, you sure about this bathtub curve? Do we know it applies? What are the age-related failure mechanisms which we can demonstrate or find that would apply to cables? It may be that they do have age-related failure mechanisms, but they still need that failure mechanism to apply and be in service. So that's my little spiel on bathtub curves.
That's okay. We got another question here. Are utilities finding it easy or challenging to justify installing continuous monitoring of cables to regulators?
I think that it's becoming more common, and I think that when you look at the cost of the monitoring system versus the cost of putting the cable in place, it's a very small percentage. And so I think that while to the question earlier to Chris on should we do monitoring of new assets versus old assets, a lot of this monitoring requires an upfront investment and making sure that there's communication conduits run, power conduits run in parallel with these transmission circuits. So I think that the appetite is there. There's specific language in the infrastructure bills that have come out talking about monitoring and cable monitoring. So I think that there's more of an acceptance of looking at this, but probably one of the biggest drivers for it is the general cost of putting in underground transmission is pretty high. And so when you look at it as a ratio of monitoring versus the infrastructure cost or replacement cost, it looks a little bit more attractive than certainly than if it was being applied to an overhead transmission project.
Yeah, the cost of underground transmission is really high.
Yeah, I mean the overhead, average cost overhead is 390K per mile, whereas underground can be up to about 2 million a mile, and that is without any of the NIMBY considerations or permitting, which can also add lots of cost and time to a project.
Well, are the losses greater if it's underground?
Say that again.
Are the
losses for-
electrical losses greater for underground as opposed to overhead transmission?
If you're thinking about traditional line loss, I'm not
Yeah.
sure. I think that, most of the studies that I've looked at that sort of compare overhead and underground, even from a reliability and cost, don't really weigh one way or the other as to what is the advisable solution. There's a lot of externalities to utilities that will drive them to decide to bury or hang overhead different lines. So I'm not sure it's really a line loss cost, but I think from a condition monitoring perspective, I think it's the project cost and replacement cost that makes putting in a monitor for a small percentage of the actual project cost more attractive than for overhead.
Okay.